Hello, my name is Ariel Louis. I'm a mechanical engineer here at UCI. I am UAV Forge's current project manager, and I've been with the project for 2 years. During the competition, I'll be the judge's point of contact and will assist the structures team in assembling the aircraft.
Hi, my name is Prad. I'm a fourth year at UCI and this is my second year on the team. I'm the software team lead, and at the competition I will be working on image recognition and monitoring the ground station.
I'm Sunny. I'm a senior at UCI. And this is going to be my first year on the team for UAV Forge. I'm part of the software team and I'll be monitoring the ground station application at the flight line.
Hi, my name is Kristen O'Connell and I'm a third-year mechanical engineering major at UCI. I've been on the UAV Forge project for 2 years, and on the development team I work with structures and propulsion. For competition, I will be assuming the role of team captain.
Hi, my name is Chiwei Chen. I'm third-year electrical engineering major here at UCI. I have been on UAV Forge for almost 1 year. My role on the project is the chief engineer of electrical engineering and computer science. So my main role is to supervising and help the avionics team and ground station team to accomplish their job. And also I'm the main coordinator for the autonomous flight test. My role on the competition will be basically coordinating all of our subsystems and make sure the airplane is delivering the text that we want it to deliver, and also make sure that there's no accidents happens during the flight test.
Hello, my name is Kyle Gramai, and I'm a third-year mechanical and aerospace engineering student at UCI. I've been with UAV Forge for 2 years, and I worked on the development team working on the propulsion system. On the flight line during competition, I will be working with a mechanical team to make sure that our aircraft is ready to take off.
Hi, I'm Daquan, and I'm a senior mechanical engineer here at UCI. I'm the mechanical and aerospace team lead for UAV Forge, and I've been on the team for 1 year. I have 1.5 years of experience working with unmanned aerial systems, and for competition, I'm the mechanical team lead, and I will be making sure that the plane structure and propulsion system will be ready for flight. Our competition aircraft is a trainer called the AeroWorks GT. It has a detachable 88-inch high wing with a tricycle landing gear configuration. The fuselage volume is approximately 800 cubic inches, and the plane uses a 20x8 propeller with a 290 kV electric brushless motor that is powered by a LiPo battery. The plane internal fuselage houses a Pixhawk, RFD 900 telemetry radio, Futaba RC receiver, GPS equipped with an arming switch, Sony camera, Raspberry Pi, and a dual-band image transmission antenna.
Here you can see a graph of our planned tasks as well as our expected performance in each. We have rated them all on a scale of high, medium, low, where low means that we have a low expectation of doing this well, whereas high means we are very confident that we can perform this task without any error. As you can see on the right, all are highlighted as yes, meaning that we will attempt this task. 7 weeks or so, we have done 17 flights that have had autonomous features. Now, per each flight, the time in autonomous mode varies as the duration of the flight itself varies. But for most of the flights, we had around 80% of the flight time in autonomous mode. Most of the time in manual mode was spent during the landings before our landing procedures for autonomous mode was well tuned. Generally, the landing procedure takes around 1 minute. This means that if a flight was only a minute long, the landing procedure would take around a minute, so that would mean that only 50% of the time would be spent in autonomous mode. However, most of our flights were longer than this, meaning that most of the time was spent in autonomous mode.
Alright, for autonomous flights, for us to tune our airplane, Pixhawk offers auto-tune mode. So when we set that mode on and ask our pilot to fly in sharp maneuvers, so sharp dives up and down and sharp turns, so left and right, the Pixhawk would automatically tune parameters so it could fly optimally for autonomous flights. And as for takeoffs and landings, we just change those specific parameters until we see a good takeoff and landing. For waypoint accuracy, our software has the ability to easily customize and modify waypoints. So we could add and delete waypoints, we could change where they are, and we could change the parameters for them. So when our plane attempts these waypoints, the plane will go towards the waypoint, and it'll try to hit its waypoint acceptance radius, which we could change. And once it hits that acceptance radius, it'll go on and try to hit the next waypoint. Because our waypoints are very customizable, our plane shouldn't be able to be forced to do any sharp maneuvers or impossible tasks, which will lead to waypoint misses, and so it won't miss waypoints, and the average waypoint miss error should be really low, as long as we, the operators, set a good waypoint course mission, or a good course of waypoints that the plane should easily be able to handle. In the event that the waypoints are poorly handled, as in there are waypoints that are set on the maps that the plane would have a lot of difficulty in handling it, then there are features in the PICSOC which would accept the waypoint outside of the acceptance radius. For example, if there's a sharp turn that the plane cannot make for the waypoint that has an acceptance radius of 2 meters, the waypoint would just skip that waypoint and say that for that particular waypoint, it accepted it at, say, 50 meters instead. And I'll just carry on to the next mission. For obstacle avoidance performance, it's basically the same concept of our highly customized, customizable waypoint feature. So when we see an obstacle on the map, we could just set waypoints around the obstacle, and theoretically it should be able to handle the obstacle avoidance with no problem, and it should be very easy. For our testing, we just set an obstacle on the map, and we set waypoints around it, and we verify that the plane does actually avoid the obstacle by flying it, and we see on the map, on the trail, that it goes around the obstacle, and the plane doesn't actually go inside the obstacle radius.
How the imaging system works is that there's software on the ground control laptop which sends signals to the software that's on the Raspberry Pi to take the image first, and then after download it. And all this happens over the wireless Ethernet bridge that connects the two. So how the tests were conducted was, first they had to be conducted on the ground, of course. And what we were generally looking for when in these tests was the speed at which the whole process happens, from sending the signal to take the picture and receive the image onto the laptop. The full image, by the way. It's the full image the camera's capable of taking, which is like a 4,000 by 6,000 JPEG. So we guarantee to make sure all those pictures come through. And the piece of data that we take as we're recording is the time. Yeah. And then we vary that by the distance. And so how we did the test rig on the ground was we set distances and went further and further and further away, and see how that influenced the data speed. And then the second test was an actual functional test on the plane itself, to where could this event happen on the plane itself, and we were able to take images on the plane successfully, and were able to take some target photos as well. It sends the full image, and that's through the software using a certain protocol that guarantees every single piece of data comes through. And there's a way it's arguably takes a little longer because it's guaranteeing everything comes through. There was an option we could have done where we could have set a different protocol, which just sends the data and then has the other end receiving just as much as it can. And that would have been out of haste. But the method we're using guarantees each photo comes in complete. No missing pixels, nothing.
So I'm running the test image on the that I just sent Arrow here. So the way it works is it uses this thing called surf detection, which finds like regions of interest. So if you see like the red dots in here, those are like the regions it detects that are like of importance, right? So first I converted to the HSV color space, which is it's better for colors pretty much. And then it finds those, right? And then for each one of those images, it looks around it and see which one has the greatest response, so you get no duplicates. So you can see there's 3 of them right there on the one with the Y, but using some algorithm, I just take the one with the most confidence and then just throw the most response, and then just throw away the other 2. So then I don't have any duplicates. So once I get that image right, I crop it out, and then I run I do some more filtering, and I run k-means, right? So what k-means is it filters out the color for every pixel, so every single pixel goes to one of whatever k number of colors that is closest to what it represents. So in this case, I chose k to be 3. So there's 3 main colors in here, like some kind of brown, some kind of like greenish, and then some kind of I don't know, gray. So every single pixel turns into one of those 3 colors. Is why we get this image here. From this image, actually, I guess this one's a better one. So there's a green, there's an orange, and then there's a red. And then from those 3 colors, I find the contours of it, which is pretty much like the edges. And then I use those edges to crop out the image and see like what shape it is. But it's kind of difficult to crop it out because you got like the ones inside and you got to draw it out, so you got to create like a mask. So I was able to get the whole image, but what I'm doing now, I got the image of the shape, right? I want to filter out the outside and get just the shape on the inside. So what I'm doing right now is filtering out the shape and getting just the letter, so then I can put in the OCR model. So I create a white mask to put it on, so the shape background mends with the white background, so now you get just the letter. And then you do a bitwise knot in order to get just a white image of the letter here. And then this is the image that will go into the OCR for the letter, and that's how we get our results back. So the way the localization works is it takes whatever key point that return a letter in a shape with a high confidence of above 80%, and it takes those images and finds the coordinates of those, and then does some math to subtract it of the coordinates relative to the plane and the camera when it took the picture, and then with the coordinates of the plane, it will be able to geolocate where exactly in the range of the field that the plane took the picture to get those coordinates, and then it will find the longitude and latitude from that.
Over the past couple of weeks, we have attempted the airdrop challenge under competition conditions 4 times. Our average error was 66.25 feet, with a minimum distance of 39 feet away from target and a maximum distance of 119 feet from our target. We are confident from these manual tests that we will be able to complete this part of the task.
We had performed 1 mission demonstration test. In this test, we attempted the autonomous takeoff, landing, waypoint capture, obstacle avoidance, and the air delivery. The image capture and transmission system was not attempted due to technical difficulties during a pre-flight check. Each subsystem is separately tested and analyzed at previous flight tests or during pre-flight checks. After the mission demonstration test, we conducted an evaluation based on the rubric seen in the rules. For the timeline, 20 minutes will be enough time for the team to assemble the aircraft, create a mission, and set the aircraft on the runway. For the autonomous flight test, the auto takeoff and landing was accomplished successfully. The waypoint capture had less than 25 feet of error deviation, and there were no manual takeovers during the flight. For the obstacle avoidance, only 1 obstacle was tested, and given that the minimum turning radius of the aircraft is 27 meters, therefore the aircraft is able to avoid the 30 feet to 300 feet cylinder obstacles. The scoring for the object detection, classification, and localization was graded as 0 because we did not have a working image capture system during the mission demonstration. For the air delivery, we were able to perform 4 manual drops and average the error distances to get the results seen above. Finally, the operational excellence had a full score because the competition team performs on a AMA regulated airfield.